So we're at the data 5321 just to ensure you're all in the right class and I'm at the right class. The course title is Statistical Machine Learning, and that's the entry level for the course. I assume there's going to be a second one too, since it has one in it. Just my guess. I haven't been in the courses so far that long. So many of you mentioned that you're interested in the data, in the machine learning. Nobody mentioned specifically the statistical aspects, which gets me a little bit worried. But we'll see, all right? Especially, and you're not wrong, so if anyone wants to kind of walk us through this meme and say what it shows, what would it be? I guess it explains itself, right? So nobody's interested specifically into statistics. Many people are mathematicians, right? Which I love it. But many people, in terms of audience, when you see them, when you see the beauty in the statistics, the relation between different equations, the way you can get sense of the data is perfect, is nice. But when you have the applications where you want to have the audiences there, many of them don't appreciate it enough. So people kind of frame the statistics around machine learning to get kind of sense of a better framework around what their predictions are, what their findings are, and the insights that they are sharing. And sometimes they don't get enough attention as well. So things get really exciting when it's AI based, right? So the same crack on the wall, but it's ChatGPT, then there we go, it's exciting. But there's also other reasons for that. We'll get to that. We'll scratch the surface of why things are interested as we go up in the application layer slightly today, but through the course we'll get there. Before we start, I haven't introduced myself. My name is Sohail. My last name is Jamshidi. For you, I'm Sohail. You can call me Sohail, which is the easiest thing. Let's zoom in into who I am first. So, as I said, my name is Sohail. The best way to pronounce it is not a common name, so I help you pronounce it. It's Sohail. It's like it was so haily that I couldn't drive to work. But the meaning of it, I promise, has nothing to do with weather. It has a deeper meaning in it. So it's a Persian word. I'm from Iran. It's a Persian word for the Canopus star. And if you never heard of that star, it's fine. It's the second brightest star in the sky. So usually people talk about the golden star, the North Star, but this one's the second brightest. The fun thing about it, and why my parents maybe named me after that, is that the Canopus star is so close to the horizon, you won't see it more often. So you have to be in the right spot, right time of the night, and maybe no obstructions on the buildings and such, so you can see it. So in our culture, when someone is not, you don't see someone that often, you mention that, hey, you became Sohail's star. And here we go, like a couple of decades after, without telling you what my age is, I'm here in the US, my whole family are in Iran, so I'm the real Sohail star now these days. I don't get to see them, and they don't get to see me too. I have a PhD in computer science, and anyone can guess from where? Yep, from University of Oregon, Southern Eugene. I was once a doc, sometimes a doc, not always, but there we go. I also have a master from there. I got my master's from Isfahan University of Technology back in Iran. I also got my, bachelor from there and the master's from University of Tehran. University of Tehran is they call it mother of universities, one of the best universities in that country, big enough that they put it on the larger denomination bills. The entrance door of it is there. And currently, I'm working as a machine learning software developer engineer, development engineer at Amazon Web Services, AWS. And when I mention that, if the first thing comes to your mind is the packages that get delivered to your house, we probably need to talk. AWS does more than that, so it's the cloud provider service for sure, and you heard of it probably as you've been working on. All of these things that I mentioned, like where I've been, what I've done, what I'm doing currently, not that I mentioned what I've been doing, but basically so you know that you have some sort of background in me, that I'm hoping that I can be the best teacher for you. At least I can convey the message of this course to you. So the reason that I mentioned that part of the class. My email, you can see it on the class webpage, but it's also here. So if you have any question, you have any suggestion, just like the door that I delayed closing it and then I regret it immediately. If you have any question or suggestion, just let me know. If anything's bothering you, not letting you learning anything in the class, would be better not to tell me now, but send me an email, at least from next week. I'll do that. Seems like I have an office at the same building, 528, but I'm wearing kind of a couple of different hats, so I'm usually not at my office. I also working full-time, relatively, so I try to be available though through Zoom, and I was thinking about the office hour to be 1 hour after this session, since we are all here. If you don't have anything to do or have questions, I can stay longer and then we can discuss it. And also I was thinking about having one on Tuesdays, because your homework's gonna be, the deadline will be midnight of Tuesdays every week for the next 9-10 weeks. So I thought that by that time you get through the homeworks, you've done what you know about, and you have all your questions, so it's better to have the office hours by then. Tentatively, I might change it a little bit, depending on how it goes, but for now, that's how I'm setting up. Hopefully I haven't talked so fast or so unclear, so if you have any question, let me know. No? All right. So let's zoom out. That's enough about me. I told you I will talk about myself. Maybe you didn't expect it to be that long. Let's zoom into the class. Any guess which letter we'll zoom in? Any wild guess? Which one? S? Sounds good? That's good enough. But I was so naive, so I chose A to be the first letter of the alphabet. So we'll go there. So course structure and rules, there are not too many rules, to be honest. Just try to learn as much as you can through the course. But I have some suggestions and some requests for you. One is that I expect you to be present into the class, both physically and mentally. And what I mean by that is that it's important to be part of the class. Even if you're not paying attention, try to be in the class. It helps me to know that I have the right audience to talk about. And also for you, you hear some concepts that later for the midterm, for the final, you're going to read it. At least you remember something. Your mind going to passively grasp on some of the concepts, although you might be busy for other stuff. So try to do that. But also, we are at the Statistical Machine Learning course, right? So I can prove my point with a couple of data and some plots, and don't think that is made up. So there are some researchers somewhere probably that showed that the final grade has some relations with attendance. So those who have attended more into the class, they got a better final grade. And I know the grade is not everything that you care about, but it's kind of nice to have it, right? A better final grade. So that's yet another reason to prove it. And the second thing that I'm going to ask you is that know the relation between discipline and motivation. I don't want to motivate you. I'm not a motivational speaker, but I realized in my life, and the reason that I'm here now is that sometimes motivation is really good at the beginning. I love that you have both of them, but motivation goes away. So first session, right, you're excited to see what the course is about, who I am, like who is this guy is teaching this course maybe, or you want to know about, and then I bored you in the first session, the second one, same. Things get really serious at the middle of the course, so you start kind of not being as motivated as you should be. But if you have the discipline, you force yourself on Wednesdays afternoon, I have a class that I have to go, maybe even suffer, maybe enjoy. So it helps a lot. So you can sum both of them, like have your motivation, that's amazing, but also have the discipline on it. And it helped me a lot in life, and I'm also guilty of not doing it for many different things. So maybe this quarter we can do better with that. We're also gonna have a lot of fun. We're having class activities, which is a good name for having quizzes. Not really. I'm not going to have quizzes, but I will time to time ask a question, open-ended question, so get your engagement into the class. Then we have weekly assignments, so every week you're engaged with this course. Don't forget about the course through the week. So it's not just Wednesdays we gather. We have midterm on mid-February, and we have final exam on the third week of March. All right? Anything else? Oh, and also check out the course page. So I put some time put together the course page. I think I put together everything. I think the links are working. Many of the modules that I copied over from the other session of this class from Mondays that Professor McLean is teaching. So if you see some inconsistencies, like, let me know. I will fix it, but you'll see his name around the Canvas page around. So he has the copyright on a lot of the materials. But I tried to use ChatGPT to generate some pictures to kind of differentiate this course, this session of the course from the other one, and make things better slightly. Through the course, we'll be talking and mainly go through the materials that we have in this book. It's available free. If you have checked the course webpage already, you know the PDF is there. You can download it. You can use it. We'll go through that. And it's basically focusing on programming with R language. Do you had any exposure to R language so far in your life? Maybe half of the class? Perfect. R is not my strongest suit. Maybe I wrote some codes with R time to time. If it was Python, I would have loved it, but I have nothing against R. So we'll go through it. We learn with each other, which might be even better, so I can walk in your shoes as well. All right, zooming out all the way from my name, from letter A, from the course rules and such, to a bigger picture. So this would be all the items that we will go through today. A lot of items, I know. So ready to get started? Any question before we do? All right, let's go. So statistical learning, statistical machine learning is the course. We start with this statistical learning and what it means. Basically, statistical learning is about the process of understanding patterns and relationships. Two things, patterns and relationships in the data to make, again, two other things, predictions and informed decisions. Not always, so some of you mentioned the sports prediction. Chris mentioned it, I guess, I believe. So you mentioned that you're into predictions. You want to do it in the financial aspects, in the sports, in other domains. Not all people using machine learning for predictions. Some of them are basically for informed decision. I promise not to talk a lot about attendance and the final grade, but going back to that plot, that famous plot. So we don't need to predict your final grade based on your attendance, but it's sometimes nice to know and make an informed decision about probably not coming to the class or coming to the class. So that's one of the reasons that we can benefit from the statistical learning. Before this class, in other courses, 5300 maybe, and the other one, if you already passed out that course, you had some exposure to the linear regression. Is that a correct assumption? Perfect. So let's just start with that, something that we all know about it and we've seen it before, so we start and building up from there. Linear regression, and you will have the slides. If you feel that you need them later, I will share them later. They're not currently in the course since I wanted you to first-hand see it from while I'm here. So I will also share that one. So linear regression is one of the main foundational methods in statistics learning, statistical learning, that helps us to model the relationship between an input variable and, in many cases, a single output variable. So we have input and output. We want to see what takes us there. Probably worth it. It's a famous method. It's probably worth more than a sentence to know about it and kind of review that. So let's zoom into one of these dots. I'm not asking which one, so it could be any of those ones. So getting again back to that plot that I know you don't want to see it again, and I'm trying not to bring it up that often. So there is a dependent variable, an output, which is a final grade. It could be your happiness. Doesn't matter, right? At the end of the course, of course, right? We call it dependent variable. Why is it dependent? Because it depends on different variables. The final grade, it depends on your homeworks, on your attendance, your attention, your efforts, a lot of different things, right? And also how easy the questions are in the exams. And the other things that determine the value for the dependent variable are called independent variables. They call also inputs, variables, features in many cases, right? So they have different names, but here's the thing. So dependent, independent, and an easy way to kind of memorize it, to get a sense of it, is to know that the one that we are looking for, the output one, gets its value based on a relation from the input. Linear regression is basically, it's called linear regression for a reason. The formula for that model is basically a line, which is the output equals mx plus b. M would be the slope or the rate of changes, like how fast would it change if you attend the class. If you attend all the classes and also other neighboring classes, would you get the best final grade? This equation would show it to you. But what if you don't attend any of the classes? Will you get 0? Probably not, right? You still can read the course, you can see the slides, and you can do a lot of other things, right? Based on what you learned before in the industry, your experiences and such, but you don't necessarily, even if you look at this washed out line, it wouldn't touch 0 and 0. So we have B, which is called the intercept, I believe, or intercept to pronounce it better. So that's the reason. So when X is 0, we have B to help us to have the right notion about Y. So that's all about linear regression. One line, two variables, coefficient, I would say, and then we have dependent variable, independent variables. Good to go? Yeah? Awesome. So let's zoom out again. Hopefully you don't get motion sickness after this class with these slides. I might get some, but with the bigger screen, so I was designing it on my laptop. It was a smaller screen, it's fine, it's contained, but when the bigger screen is there, it might be not as helpful. Anyway, learning linear regression, not learning, is one of the instances of a bigger family of methods which are called supervised learning. Again, the names are so intuitive. Supervised because someone is supervising the process, and that someone is you when you are training a model on the data. So you are basically supervising a model to make sure that you get the best model out of the data. So you're going through the process of basically training a model, looking if it's good or not, and then making it better and better over time. We call them supervised learning. Let's see if I missed anything on the text. Probably not. So we have a feedback loop basically to make it better and better. The general setup for the supervised learning is we have the output variable. Remember the final grade or your happiness during the class. We have a couple of input variables, x1, x2, xp, all the way to xp, which we call collectively, we call all of them as x, which is our data sets, right? We have x1, for example, is your attendance. x2 is the amount of effort you put after the class to learn the material. x3 is your performance in the midterm and final, so on and so forth. And also how well I'm teaching the class. It's not all about your effort, so I might not be able to perform well in the class. So that's one of the x's. Combined all together, it would be x. And then we want to estimate a function, which we call it f of x or fx. And that one describes the relationship between the independent and the dependent variable. In linear regression model, what was the f of x? If you can guess. Perfect. mx plus b would have been the f of x, which is the relationship, the model that we figured out there. And epsilon, I didn't have the epsilon character for whatever reason, so I used e. So the epsilon that is basically represent the residuals or the errors, or the random errors, hopefully. And broadly, we call f of x the systematic information that x provides about y. So f of x is our model, is the systematic information we get that x provides for the y. And e is the random error. All right, two equations we went through, y equals mx plus b. Second one is y equals f of x plus epsilon. Errors, the model, and the systematic information. Any question so far? I keep asking before because personally when I have a question, I keep thinking about that question. So I don't listen to the rest of the stuff. So I want you, if you have any question, just let me know. And also one thing that I forgot to mention, I would love that you ask question even if the question is so obvious and I have the answer right there with the biggest font. Feel free to ask it. It helps a lot. Not only you, it helps the rest of the class as well. Many of the people in the class might think that they got the idea, but when you ask question, you realize probably we haven't got the idea, including me. So, all right. Sure. Thank you.
Sorry, so for the y equals f of x plus epsilon and the white box, so that's like from my understanding, that's like any supervised learning, not just linear regression, right?
Exactly. So that's basically the general setup for that. The general setup for that is usually when we think of any supervised method, we are thinking about that, kind of categorize that as finding the f of x. That's a process of working with the supervised method. Specifically for linear regression, I might kind of confuse you about that one. The f of x, the literal model that we are using instead of f of x, or we found for the linear regression, was y equals mx plus b. So that was the something that would replace this one. Then if we use another supervised learning method, then the f of x would be something different, might be something really fancier. That only a single line. But yeah, that's a good question. Exactly. That's a generalized way of dealing with the supervised learning methods. Yes, a link, right?
Yeah. I was just wondering, when you say supervised learning involves monitoring how well the model predicts the output, does that always involve using some sort of test data, or are there like other methods we're going to learn for monitoring?
Very good question. I'm so eager to answer your question now, but I have a whole slide about that.
Okay.
So if I continue talking about it, I'm going to spoil the rest of it. But short answer, since I mentioned if you have a question, you would probably know the rest of it. That's exactly the process. So we have to focus during the process. We are finding, so actually it's so good question that I should go back. Right now, I told you to prove my point, I draw a line to say that, hey, if you attend the class, you will get the best final grade, right? But it could have gone anywhere. That line could have been like downward even, that if you attend more classes, you get worse results in the final grade, right? So the process involves into figuring out what the error is when we say this is the model that describes our data, and keep improving that. There are two types of different errors that we will discuss in depth, and we are trying to reduce that one. And you also talked about the test data, which is important, that which data we are looking at when we are assessing the data, because of a lot of other issues. So we'll talk in depth. But supervised learning methods, the main goal is to bring the error down, to have a better model. And what we call a better model, there are some aspects we will talk about that. All right? Did I roughly answer your question? Awesome. If I didn't answer your question before the break we'll have in a couple of hours, let me know. Okay? Any other question? Good. Then, when we say supervised method, there should be an unsupervised models as well, right? So unsupervised learning, here, there's no output variable to predict. So, for example, we want to mention that I'm looking for a model to automatically assign the students in the class into different groups. Let's say for a group project or an assignment. There's nothing that I would predict. There's not necessarily any metrics that would let me know that those grouping was successful or the best, because I don't have any data about it so far, right? In such cases, we will go with another family of the models, which are called the unsupervised methods. One of the most famous ones, the methods for unsupervised methods, are clustering. So grouping people, grouping data, grouping products into different things, those are all clustering. Finding what are the similarity between the items in your data set and form a cluster and let them be processed together. Let's assume that way. Or if you have like a students in the class, let them work together and hope for the best that they will do great. The course focus here, 5321 and 5322, mainly they focus on the supervised learning though. So if you are super excited about unsupervised learning or you're so attached, that's your last chance to leave this course, unfortunately. Because otherwise we won't talk about them that much. But good news is that 5322, which is the course after this one, if you're interested to get it, has a section about unsupervised learning methods. So there's some slight hope that you get into those. All right, we started, so I used to review things over and over. We started off with the linear regression, something that we all know about it. We discussed about two family of models, supervised, unsupervised. Good. Let's go. You remember we had all these up and downs. We're just one of them. It's done. Now we are on the upside of that. We talked about the predictions versus having informed decisions, right? We changed the name of informed decisions into something more formal. It calls inference. So there are two goals for supervised learning: prediction and inference. Prediction focuses on quality of the predicted values or y-hats. And the inference is basically trying to understand that what is the relationship between the input and output. And basically the model that we say, the relation, the line that I drew over that plot, understanding that one. Prediction, let's get to the first one, the prediction. An example of that is predicting the load on Amazon Web Servers on a daily basis. Like, what would be the load? So people at Amazon should be kind of prepared for that one. So that's for that purpose, we're going to do basically the prediction, supervised learning, and such. The key concept here is a prediction error. The error that Elise was also talking about is basically the difference between the predicted value we had with our model and the actual model that we see. So we say that tomorrow everything going to be quiet, no load on the servers, but tomorrow there will be a peak. So the difference between the peak and what we have predicted would be our error. And then the components of the prediction error, there are two different error types. One of them are reducible. One of them is that we had a bad model, so I maybe guessed it myself. It's not really it's not a polished model that I used. So that's a reducible model. So if I use a better model, I can reduce that one. That's the goal. We have to do that. And the second one is irreducible error, which is caused by the randomness or unobserved variable. Two things. The data we gather, it might be too random, right, that we cannot really get a sense of it. So the data is not good, regardless of whatever you use, whatever model you use, you're not going to get any relationship out of it. You can think about those dots. If they were all over the plots, attendance versus final grade, it's really hard to say which model would predict it if it's like covering the whole plot, like all the 2D criteria of that plot. But otherwise, we could have a model to describe that. And the second part of it, so randomness is one of the reasons, and the unobserved variables is the other one. So if I have a model saying that you will be this much happy, or this will be your final grade, based on only attendance, I'm losing a lot of different other variables that would affect it. What about the way that I teach? What about the material that I cover? What about the homeworks you do, right? What about the weather? All those sorts of things, those are important. So if you don't have them in our model, then it's obvious that we will have off predictions. So what can be done in this case? For the irreducible errors, what can we do? Especially if it's not due to randomness, if it's due to unobserved variables. Any guess? So I reframe my question. Let's assume that we have some data, we are training a model, we've done our best, but still we are not getting a good result. The errors are so high, and we think that there might be some other variables we can use. What can we do? Probably use those variables, right? So figure out what other variables we can find to help us. So in financial domain, there are a lot of interesting things that they are doing. So when they are predicting the stock values for a company, you probably heard about it in the news maybe some years ago. People were using satellite images of parking lots on businesses like Kohl's, like Macy's, to know how busy they are during peak times. And based on that, they were predicting how they will do in the end of the quarter. So that's one of the smart things. If you think about like the sales, you would have think about a lot of different variables, but looking at the satellite images of the parking lots, probably wasn't one of the first things you would think about. So there's always ways to improve or have the unobserved variables to have a better prediction. You probably heard about feature engineering. That's loosely related to this aspect of it. So two types of errors. The second one is kind of important. The first one comes naturally. So when you say that this is the best model I have, first question people would have for you is that, what's the error rate? So you have to answer that one, but the second one is kind of hidden there. And the objective here is to minimize the reducible error, quantify irreducible error in order to have better feature engineering. All right? So let's get to the inference. I had that plot. I forgot that I will talk about it here too, but that's what I was talking about. So for the prediction error, the first one, the reducible error, if I had drawn that washed out line there, instead like I had the red line, I probably would have been able to do better to predict it better, so reducing the error. So the first category of the errors would be reduced that way. Let's get to the inference. Inference is, basically inferencing is talking about understanding the factors. Instead of predicting what would be the load, is understanding what are the factors that lead into having a load on the servers of a website. There's Amazon as an example, right? What are those factors? What can you think of? So we're thinking about the load on web servers. What could be the factors? Holiday, people start shopping, right? So it's expected to have some peaks around the holidays. What else? What is it? Time of the day, exactly. People probably wouldn't do that after midnight, though some people get midnight shopping habits as well. I did. And someone else mentioned something. Sales. There are promotions going on, Prime Days, Black Fridays, right? It would also affect that. So all these aspects, as I mentioned, it helps you thinking. So any problem that you face later when you're working on machine learning problems, regardless of which problem you're working on, it's always good to have the practice of thinking about the ways you can improve it, the new features that you can use on, the innovative things that you can bring to your model, because one variable can make the differentiation between the model you're working on and the rest of the world are working on. So it's not necessarily about the parameters or the billion number of parameters that people are working. I will have some examples for you about that one as well. So smart thinking about, not smart thinking, innovative way or creative way about thinking about the features, a lot of them helps you a lot. So that's the reason I'm asking this question. So we are kind of practicing with each other. So the objective here in the inference is that we tend to interpret the reasons that drive the actionable insights. So in this case, the outcome is that instead of saying that tomorrow the load on the Amazon web server is going to be like 50% more, we want to say what are the things. We want to say tomorrow, due to X and Y and Z, the load will be cut in half. Or if we want to cut in half the load on the servers, we can cut on the way that we are like improving the performance of databases, something like that. So these are like insights. And executive level people will enjoy having it because they are actionable. So you can work on top of that. But there's a trade-off. The better you can predict or the better you can do the inference or interpretation, the more flexible models, they are better for prediction, they cover the data better, but it's harder to be interpreted. Like ChatGPT is really hard to make sense of, at least for you and me, to get a sense of why it came up with that sentence when you ask a question. But if it's a decision tree, you all know about decision trees, right? If and else. But about the decision trees, you look at the structure of the models, it's obvious. It's like this, 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 it led to that one. And restrictive models, decision trees, for example, is easier to be interpreted, but they are relatively poorer at making a decision. Decision trees are really hard to be kind of tailored into what we really wanted. So interpretability is an important aspect in AI/ML. If you're interested into like graduate studies or research or things, interpretability is a huge area that you can focus on if you're interested. We have some examples of the models there. You don't have to memorize them. And the reason that it's important is that you trained your model for a long time, right? And it was performing amazing given your training data. You put it on production and performs poorly, right? So they come back to you and say that, hey, what happened? What is wrong with your model? You look at the data and data looks like that. It's even challenging for some of us, maybe at least for me, to know the differentiation between these chihuahuas and muffins, right? So it's not necessarily a thing. So we have to be able to interpret the model. Though here, we should be able to interpret things from the input data, not necessarily from the model, right? So it's just an example to make sure that you don't sleep, basically. It doesn't have any information in it. But this is a famous challenge and famous challenges in the AI/ML called Chihuahua versus muffins. It challenged a lot of things back then when it was like figuring out what is cat, what is dog for the model was a big deal. You won't believe it was like only 4 years ago. And now ChatGPT can drive my car. Not ChatGPT at least, Tesla does. So anyway, but to be more serious, jokes aside, there are frameworks out there that help us to interpret even the most challenging or or most complex models like neural networks, which are not easy to know what's happening inside them. One of the interesting ones is Lime. The way that they do, basically, just assume that you have kind of crossed over lines all over, so that's your neural network. The way they do is that connect the electricity at the end of one of them and see where it lights up, and they do it so randomly and so like eagerly to be able to know which ones light up so fast, and if you miss one of them, the results of your classification is different. So they change, like they cover the eyes and see, oh, it's not covered as a dog, and then they cover the ears, oh, it's not the dog anymore. They realize that these parts of the segments of the image, for example, or input is really important for the model. So they mentioned that in order to figure out the label of this picture, these were the, you see the heat maps there. These are the most important aspects. So whether the model says that the input was a dog or cat is something, but if it's only looking, for example, at the background and it's just highlighting this part and saying it's a dog, you don't have a good model. It works, at least for some of the data, but it's not generalized enough. So it's not making the decision based on the right logic. So interpretability, again, is important. You remember we talked about f of x, and I thought that's the systematic information x provides for the y. How do we estimate f of x? For linear regression, it was kind of easier. We know how to do it, but how do we usually do the estimation? There are two types of methods that we do, two types of different methods that we try to use for estimation is parametric models and non-parametric models. Parametric ones has a specific model, for example, straight line for linear regression. We pick the parameters, we find the parameters, we have the model there, and I have the example. So slope and intercept, we know those coefficients, and we have the model. There we go. Non-parametric models, they don't assume a specific function like f, like it's not a line necessarily, but they try to find the smoothest function around the data, like moving average, one of the ways that we can name for that one. There are other methods that can be both parametric, non-parametric, as far as I know, like roughly SVR and SVM, I think examples of that. Characteristics of each, let's get to those ones. Parametric models, they require selecting an appropriate model, so you have to look at the data. For example, linear regression, you have to make sure the data is kind of linearly describable, so then you would do that. Basically the nonlinear patterns, we are not going to use the linear regression for that one. Non-parametric ones, we avoid the assumptions overall, but it's harder. So we have to have bigger data set to make sure that we capture the sense of the data better when we are finding the actual model. The focus of the course this time, you don't have to leave the course. We're going to cover both of them, I promise. So will be explored.
I'm confused about the non-parametric models. Like, what kind of task would you like use like a non-parametric model like for? When would I need to have a non-parametric one?
So for example, clustering, you don't necessarily, if I'm not mistaken, you don't necessarily have a model specific, right? For clustering the process, I will cover it in the course later, the last slide of the 2 days method. Basically, you don't have an equation for that. The way that you do it is look at the neighbors, right? So you don't necessarily have to guess it. Or Bayes classification, for example. You don't necessarily have a sense of how the data looks like. You have the...
So you just have like, oh, this is it, this is not it, and then you can just group similar things.
Exactly, exactly.
Okay.
Yeah, sure. Yeah, thanks, Akash. Any other question? All right. Supervised learning problems. Again, getting back to the supervised learning methods, there are two examples, two things I left and didn't discuss so far. I want you to discuss, to know about that ones, is that the supervised learning problems, they can be in two types. Regressions, where we predict numerical numbers. What is the outcome? What is the final grade? What is the financial gain, loss, or sports results? As Chris is interested in them, right? And the classification problems. Is it dog or cats, or spam or not a spam? We use different types of methods for that. Linear regression for the numerical ones, for example, or KNN for the classification problems. Some of the models work for both of them. Neural networks, for example, you can use, probably would get to them, maybe not in that depth, but if you know about like the Activation functions, you apply the application function, you can use it for the classification for the categorical ones. If not, you can use it for the numerical ones. Many models designed specifically for one of them, for one type of input, for example, linear regression. Can you use it to say if it's a cat or dog? Probably not, right? Probably not, unless we get super creative into problem definition. So define it in a way that we can associate it with an example. And if you can't get a sense of this picture, because it's generated with ChatGPT based on the content of this slide. So there's a car, can be categorized as home or spam, and there are some numerical things in between. So that's how roughly it understands it. But it looks good though, with a lot of issues in the text. Yeah. Mopom, yeah, something like that. Anyway, tried so hard on the title though. Good job on that. Measuring quality of the fit is another aspect. Not too many other slides left before we have the break, so let's focus on these ones. I talked about this washed out. This plot, you probably seen it for the first time now. There's a washed out line there that I said that this is the relationship between attendance and final grade to prove my point again, right? But there could be anything better than that. It might be like this one. So there is a sharp and a strong relationship between those, or it might be decreasing. So I could have like draw any of the lines. What is the reason I drew that line? Any guess? Exactly. Nice, nicely done. So we should have a measure for how well our model is performing, because otherwise we could have done any of those ones, be happy, call it a day, and go home, right? I have no sense of what is happening. So one of the common methods for it is calculating mean squared error. MSE is one of the most famous one. The way that we calculate that is basically we have that line in that plot or any plot, we have the actual error. Basically finding what we have predicted, what our model shows for any value of x, and then we have the square of that, get the sum of those, all of those data points, and get a sense of how well we are doing. So basically these are the ones that hanging to our line and trying, so this line is trying to be as close as possible to as many as data points as we can. And so you know it in a good way. The reason that they are like this way, they are not on the line or any other way, so it's not like this way, it's like this way, because for any x value, we say, for example, for number 1, what should be the actual number, what our model says, like mx plus b, x is 1, right? So we calculate y, and then we look at what actual data should be. We get the differences between the two. So we'll see how it goes. And what else? Oh, and the other thing that the Ling was asking me, it's talking about what data we are using, the testing data he mentioned, and I mentioned that I will talk about it in a slide, is that calculating the errors is really important to be done on the test sets. Because if we do it on the training set, what will happen? Someone said something. Overfitting, right? So we'll be like super confident about what is happening. It's right there, right? I guess somewhere. So it's perfect to be. So if you do it on the training set, though we are doing it at some point, if the error is 0 on the training set, the model would not perform well. I have an example here, but I guess you don't really need to have an example of that. Would you accept it from me? So if you have these data points, if you fit a polynomial like the 4th grade, right? The 4th order polynomial, it would fit it perfectly. So the MSE would be 0 for the training data using that equation. But the thing is that it's not general enough. So for any x, the data would not land necessarily on this line, right? So I know it because if I put 2 into that, it wouldn't necessarily give me that data point. So then what we call it is that it's overfitted the data, and it's not generalized enough that I can use it for any unseen data in the future. So I can put it in the production somewhere in my application. So that's about measuring of the fit, overfitting, and underfitting. Two important aspects we have related to that. So we calculate the error based on the test set, and the test set we know, usually we have a specific test set, unseen test set, is something that we'll publish our method and people using it and let us know how the error is. They're not happy about it or they're happy about it. Or we kind of use a fraction of our data in order to be used as a test set. So there are two concepts here, bias and variance. So bias, does anyone know about the bias? How would you describe it?
Like when the model is too simple to capture the relationship in the data, like the data is more polynomial than
Perfect. So if the data is polynomial, fourth order would be the best model to describe it. You use like a super simple data. Wow, that word is not coming out. So a simple model, like the first order one, right? It would be the highest in bias. So there are two types of issues that can happen. Bias is one of them. When the data is far from the truth due to simplicity of the, I really can't say that word, because the model is really simple, all right? So there's a plot there that I think it describes the issue between the variance and the bias really good. And I hope it really helps to take a look at that. So if your model is super simple right here, you'll have a high bias because you're not able to describe the truth really good. But as you increase the complexity of the model, bias goes down. However, it's not the case that you always need to improve the complexity of the model because there's another type of issue, which is variance here. And the variance is not going, is going up when you increase the complexity of the model. All right? I still have issues with these two concepts, so I really rather you to take a moment, think about those ones, and make sure that you understand the differences between the two. What is variance? I haven't talked about it yet. The definition is there. It's basically how much our trained model is sensitive to the input data. So if we try to find everything, like copy the input data so closely, we'll have the variance issue. It would be so sensitive to the input data. So if we expand the data, or if we choose another sampling, our model would not perform well as well. So that's the variance. You think you get the concept of it? Yeah? Perfect, let's test it. Here in this one, top left, how's the bias, how's the variance?
Bias is low on all these, but the variance is higher on the ones on the right.
On the top left one, how's your take?
High bias, low variance.
On the top left one, high variance?
High bias, low variance.
Okay. Any other guess? Who says both of them are low? Who says bias is low? And who says variance is low? Only variance, so bias is high. All right. So here, if you think about it, if you have a target, you're using like an arch or a bow, right, to target it. If you hit the red one, you have the best score, right? So it has to be both of them should be down. So in that case, bias is the lowest, and the variance is the lowest as well, because it's not really sensitive to anything, the way that you're throwing things, right? So you hit the target every time, and it's complex enough that helps you to hit the target. So if you look at the above one, it's right in here. It's right in here. It's the sweet spot, where you have the best combination of the both. What about this one? The bottom right. High bias and high variance. Yeah. And based on that, since it's a matrix, you can get a sense of what the other two are, right? What's that one?
High variance, low bias.
Perfect. And this one?
Low variance, high bias.
Low variance, high balance. There we go. All right. So I think at least this one give you a sense of the problem. It might be helpful, at least trying that we talk about it. We might need to think about it a little bit more. And then there's a relationship between the model flexibility and MSE. More flexible models have lower bias but higher variance. Simpler models, they have higher bias but lower variance. And both bias and variance contribute to that test MSE. The reason for that, we'll see the total error up there. When we have a little bit of bias, a little bit of variance, the total error would be down there at the sweet spot down there. But otherwise, it would be on the both sides of it. For the optimal one, we're trying to bring them down. In chapter 5, for method assessing models based on bias and variance, we'll explore them more. So it's not the only time you'll see them, unfortunately. All right. Any question before we move on? Assessing classification models. So we talked about the regression. Ling mentioned the MSE, the mean square error. That works well for the numerical ones. But if you're talking about cats and dogs and you're trying to figure out how your model is doing, numerical errors would not help you, obviously, right? So you have to have other measures. In order to do that, we look at the rate of error. So how many times I give you the picture of a cat and you say it's not a cat? We count those ones and it would be your error rate. So there are metrics in that sense that we look at them in order to say that how well the model is performing. We call them the indicator functions. I, which is basically a statement. If it's equal to the classification model, equals to the label, equals to the truth, your model outcome or not, and we kind of get the average of that. So there are different ways of finding the error. Have you heard of the confusion metrics? Perfect. So there are like true positive, true negatives, false positive, false positive, false positive, false negatives, and there are plenty of different ways of combining these ones. One of the examples is precision, recall, accuracy, which when you do any interviews, unfortunately, you have to know about them, right? And when you're assessing your model, you probably need to use a combination of them as well. It's really important to use them, not only the error rate. So your verse about using the confusion metrics as well, that's how we look at the classification models. If not, it's not a big deal. It's basically, I can basically take a look at that. I don't want to assume everyone knows about everything. So if the actual values are spam versus non-spam, if we predict it as not a spam while it's a spam, we are predicting it wrong. So we have some errors here. And if we predict it as spam, when it's not a spam, we have some errors here. Ideal is that we have the highest values here, which is not a spam. We call it not a spam. Which is a spam. We call it a spam. So we have the true positive and true negatives, high rate, and lower in the false ones. Yes. All right. Training versus test. I talked about that one. So training error is important, but test error is the most important thing. We look at the test error, and when we have a lowest test error, that means that our method is able to generalize things enough. I think I'm right at the time that I expected it to be, almost at 1 hour. So it's time for maybe a break. So let's have a break. Maybe around 10 minutes is fair. So let's have a 10 minutes break, and then we'll be back again. And I'm really happy that most of you are not like that. So you're not asleep yet. I appreciate that. Perfect. Turn on things. All right. I forgot to start recording. Anyway, so Bayes classifiers will work like that. We discussed it already. Depending on which bowl we are using, then we can predict it. But the problem with that is that the distribution of the data that we have is not necessarily known in all other situations that you face, all the problems that you have, all kinds of data that you're working with. So you cannot necessarily use it and be that confident about it. In those cases, what we will do is that we will start guessing the distribution. How do we start guessing it? KNN has the concept of doing it in some ways. In KNN, the K nearest neighbors, it can be the first one nearest neighbor, two nearest neighbor, or 100 ones. Is basically you start from one data point, you look at its neighbors and try to guess. Like if you see one neighbor of that, let's say in terms of the weather again, you look at one of the cities in a state and see how other cities are doing if they have had snow, and based on that you decide whether we'll have a snow in this town or not, then that's one way of doing like KNN. And that's the kind of the idea that how it works. I've written it somewhere there. For a given x, we estimate the conditional probability of the y by examining the closest points to that. Basically, the picture that I have here, kind of look at that. So for given any of the data points that we have, we look at the neighbors. So if you look at the, like, this is like 3 and n, so 3, look at the 3 neighbors. 2 out of 3 are green, so we assign the label of green to that point. That's the idea of behind like the KN and how it works. It kind of makes sense, but the problem is that knowing what k works better sometimes is not that intuitive. So you have to do it for 1k, 2k, 100k, 1000 of k, and those iteration takes time. And the more you have, the larger number of neighbors you look. Just imagine if you increase the neighborhood of Seattle City, it would include Vancouver, and it goes all the way down maybe to Los Angeles, right? So then we don't have like right data points that we are looking at. So LA is not a good estimator for the weather in the Seattle, so maybe we need to keep it really tight around Seattle area. So that's kind of the idea. That's all the things that I wanted to discuss. We have an example about the flights, how late they will be. We look at the similar flights around. That's the same concept as well. Here, again, we also have the notion of bias versus variance. Again, the smaller k numbers, they are more flexible models. They have high variance and low biases. Can someone explain what it means, that line? So it's this one. Why a smaller k? So if we look at the smaller number of neighbors in k and n, why is it more flexible model? And why does it have higher variance and lower bias?
K is smaller, the label can change more easily.
Right. So the model is more flexible, that's right. But also it can mimic the data, or I would say model the data more better. It can kind of follow the pattern we have in the data so closely, so the bias is really low. But it's so sensitive to the data. So if we change one neighbor in a 1 KNN or 2 KNN, then the whole prediction would be different. And that's right. Thanks for that. And the opposite on the larger k values. So Bayes classifiers and KNNs, the other two examples that we have. All right. With that, that's all the slides that I have for today. So the rest of today, the plan that I have is that I don't know about the rest of the sessions. I haven't gone through the whole course, to be honest. I haven't designed it yet. I saw the material, I went through it. I'm not sure about the timing of it, but what I'm expecting to do is that I have like at least leave 1/3 of the class for writing codes in class, kind of like having an kind of a lab session instead of having it separately. I don't know how your classes usually are. Back in U of O, we had the class session, and there was like a lab session that the TA would handle. And I used to be a TA for those courses a lot. But here, I think it's beneficial given that the length of the classes that we have. I don't want to talk for like 3 hours. So I want you to enjoy the rest of your day as well. So I talk for like 2/3 of the class. I have all the concepts around. Our second session would be lighter as far as I've seen, so that's a good news. I talk less, but it has more complex stuff in it. And the rest of it will have like kind of a lab session. So I expect you to start writing some codes in R, getting familiar with R, and let me know if you have any problems. And also we will design some in-class activities related to the concepts that I go through, so you get a sense of how it's done in R and programming languages, and you have hands-on experiences. Sounds good? For today, what I expect you to do, doing all these stages. So load the data, split the train and test, feed a model and calculate the error and answer some of the questions. And how we want to go through it. First, I want to make sure that you have RStudio set up in your laptop. If you haven't, I have attached a module in the course. Let's check the course